Welcome to a course of Production Technology Theory of Metal Cutting. In present lecture, we will discuss about the cutting tool failures. What are the different kinds of failures? What are the different mechanisms of wearing tool life, and what is machinability? So first we will start with cutting tool failures. Cutting tool failures. During machining or during cutting, after some time, a life of cutting tool reaches to its end. And the reason for this is the failure of cutting tool either by mechanical action or by wearing action. Now, mechanical failure occurs mainly due to the excessive cutting forces or excessive loading, where wearing occurs due to the abrasion action of cheap particles on rack surface of tool or on a flank surface just below the cutting edge. So during a tool life, the cutting tool works with satisfactory performance, but the unsatisfactory performance of cutting tool indicates the failure of cutting tool. So there are some deciding criteria that give you an idea about the tool failure. So how to decide that your tool get failed? So the one is that if the forces, cutting forces are increasing suddenly during the cutting, then it may be the reason of tool failure. Because if by failure or by wearing action, there may be the chances that the sharp edges of your cutting tool becomes blunt, and due to that blunt edges, there may be the generation of larger cutting forces to machine component. The another indication is that if the power consumption is suddenly increasing, then also you can get an idea that the tool is failed. Because if the cutting forces are increases, that means your power consumption will also increase. Okay. Then the cutting forces are larger because of the failure of the cutting tool. So then there may be the chances that there are some kind of vibrations at your work holding devices or tool holding devices, and these vibrations may result with chatter marks on your machine surface. So if you observe the chatter marks on the surface which you have machined, that also indicates your tool get failed. If your tool get overheated, that is also the indication of tool failure, because the edges are blunt due to the failure, due to the wearing. So there may be the chances of larger amount of friction between tool and workpiece surface, and that larger friction may result in a larger amount of heat generation, and that heat generation may causes the increase in temperature of your cutting tool. The another thing is that during a cutting, if you hear some undesired noise, So that is also due to the chattering or vibration. So that is also the indication of your tool failure. The another most important criteria to decide the performance of your cutting tool is that the tolerances that you are achieving. Suppose initially you are achieving a good tolerances as you require, but after some time, if you are not able to achieve that dimensional tolerances, then it indicates that there is something wrong with your tool. Then the surface integrity, surface quality. Initially you are getting good surface finish, but after some time, due to the wearing, due to the failure of your tool, you are not getting the surface finish as required. Your machine surface is observed poor. So that also indicates that there is some kind of failure in your tool. So these indications gives an idea to a tool engineer to regrind or resharp a tool for its further use for effective performance. So there are three major modes or causes of these cutting tool failures. One is temperature failure. So what is temperature failure? So during a cutting, there is workpiece, there is a tool, and there is some kind of relative motion between this workpiece and tool. And during interaction, due to this relative motion, there is a friction, and that friction may causes the heat generation. And if the application of cutting fluid is inefficient, then the local temperature rises, and due to the temperature rise, there may be the possibility that your tool gets softens, maybe deformed plastically, and due to that softening during the cutting, the dimensions of the cutting edges of tool may deviate, and that results in a deviation of effective tool geometry. So overall, this increase in temperature may result in an unsatisfactory performance of your cutting tool. So this temperature rise and the failure due to this increased temperature is undesired. The different tools can sustain at different temperatures. Like a carbon tool steel, it can withstand the temperature up to 200 to 260 degrees Celsius. Whereas if you are using a high speed steel, it can resist a temperature of 500 to 550 degrees Celsius. And if you are using a tool with a cubic boron nitride or cemented carbide or ceramics, then it can resist a temperature of up to 1000 degrees centigrade or 800 degrees centigrade to 1000 degrees Celsius. The another mode of failure is mechanical failure or mechanical breakage, or we can call it as a rupture of the tool point. So basically, when there is a relative motion between tool and workpiece, and if the cutting forces are high and the tool material like diamond and cemented carbide. Basically, they are in a brittle nature. So, if the tool material is a brittle kind and the cutting force is high and there is some temperature, then there may be the chances of breakage of the tool point due to the brittle failure. Okay. So that brittle failure may also leads to an unsatisfactory performance of your cutting tool. So how to resist this type of failure or eliminate this kind of mechanical failure? So one is you can use a tool material with a high hot hardness or high toughness. So the high hot hardness helps the tool to resist its properties at high temperature, whereas toughness makes the tool to resist or to sustain the cutting forces. So one can change the tool geometry, and by changing the tool geometry increase the strength of the cutting tool. Suppose, one second, this is your single point cutting tool. Okay, so this is your rectangle alpha and this is your clearance angle gamma. So if you are making this rectangle alpha and clearance angle gamma with lesser values, then you can get effective included angle, that is the wedge angle, quite larger. So if you are increasing this wedge angle, then your tool gets higher strength, and that will help to resist the cutting forces during cutting. The third mode of tool failure is wear. So basically, when tool is in use for some time, the wear is an evident. So basically, three mechanisms are involved for a tool wearing action. So first one is adhesion wear. So what is adhesion wear? One second, I need to sketch. So during cutting, suppose this is your workpiece and this is your tool and this is your chip. So during the cutting, there are some chances that some fragments from the chips get welded over here on the rack surface of the tool, and these welds are get broken after some time due to the relative motion between your workpiece and tool. So whenever these welds get break, there may be the chances that some of the particles from this rack surface of tool get detached and flow away with the chip and causing failure of tool. Another thing is that sometimes the particles detached from the leakage of wave may also overflow here on machine surface. Okay? And that also causes the detrimental effects on the machine surface. So this is the wear due to the adhesion between the chip and tool. That is due to the formation of wave as the higher temperature due to the friction between tool and chip, and sometimes these waves get detached or break due to the relative motion. Second wearing mechanism is the abrasion wear. So that is due to the detached particles from the chip that may abrade over the surface of rack, or maybe by overflowing of that particles on a machine surface may cause the failure on rack surface or on a flank surface. But basically this is due to the abrasion action, mechanical action between a tool face and the particles detached from the chip. This abrasion may cause the failure of tool. Where the third mode of wear is diffusion wear. So sometimes at high temperature the atoms have a tendency to move from a higher concentration area to a local concentration region. So if during a cutting the tool atoms move from the surface of the tool to a work surface at some temperature, then that may result in a weakened surface of a tool. So that is the diffusion wear. It rarely occurs, and the rate of this kind of wear is very less. Mainly two types of wear occurs in a single point cutting tool used in a turning. So one is the crater wear and the another is the flank wear. So what is crater wear? So suppose this is your single point cutting tool. So you can identify that this is your rack surface, this black one, from where your chip will flow during a machining, and this is your flank surface that is just below the cutting edges. So one wear is crater wear. So the crater wear generally occurs on a rack surface, whereas flank wear generally occurs on a flank surface. Now, how this wear occurs? So during a turning, during any cutting, your chip will flow from this rack surface, and if the chip is in a continuous form with a ductile workpiece material, then there may be the larger chances of the interaction between this rack surface and your chip. So the particles that are detached from the continuous chip may abrade this rack surface. Okay, and due to that abrasion, there may be the chances of formation of some craters on this rack surface. So that is the crater wear. So the abrasion action of that detached particles creates the crater, and the depth of that crater will quantify the amount of crater wear. So the crater wear is generally measured in terms of the depth of crater formed by the abrasion action of particles that are detached from the chips. So you can see here in figure, let me give 1 second. So here you can see that this is the rack surface, okay, and this is the crater formed due to the abrasion action of particles detached from the chip, and this makes the crater like this. So if we see this crater from a top surface, then you can see the figure like this. Okay, so in this view you can see this is the crater. So that crater wear can be measured in terms of depth. If you can see here, this KT shows the crater depth. If you take the cut section of your tool, then you can measure KT, that is the crater depth. Now another is the flank wear. So this is your flank. So whenever the particles detached from the chip, there may be the chances that during the cutting the particles may abrade on a flank surface, and due to that abrasion, some material loss of a tool takes place from the flank surface, and that refers as a flank wear. Okay, so in a figure you can see this is your flank surface, and some of the particles that overflowed from here to here, and that may abrade the flank surface, and the wearing takes place on the flank. If you observe the three-dimensional view, then this is your primary flank below the primary cutting edge, this is your secondary cutting edge. So this red surface shows the flank wear. Okay, so this depth of flank is termed as a wear length. So you can quantify the wear, flank wear, in terms of this wear length. Okay, if you can see the cross sectional area, then you can observe that this is the weir length. Okay, up to which depth the wearing takes place on a flank surface, that is called as a weir length. On a top view, this is the crater weir. Okay, so in short, basically two types of weir. One is crater weir, another is flank weir. Crater weir and flank weir both occurs by the mechanical abrasion action, but the crater weir occurs on a rack surface, whereas the flank weir occurs on a flank surface. Crater weir will turn in the form of crater depth that can be seen from top view and measured from the side view, whereas the flank weir is termed as a weir length. The depth of the weir is termed as a weir length. So generally the profile of flank weir is observed as shown here. Suppose here this is on an x-axis time, that is the machining time in minute, and on a y-axis there is a flank weir, that is in mm. So if we measure the weir at various machining time and try to draw a plot, then we can get the profile like this. So here this profile of wearing is generally divided in three parts. So the first region is the region A, another is the region B, and the third last one, that is the region C. So region A is considered as an initial wear when the rate of abrasion or amount of abrasion by the particles detached from the chips on a rack surface is quite large. Then after region B, the region B is considered as a normal wear, as with increase in time the rate of increase in wear is constant. There isn't any rapid jump in increase in wear, whereas the region C is the rapid wear region where the wear increases very rapidly with respect to machining time. So in short, this region C is the rapid wear region, B is the normal wear region where the rate of wear is normal, and A is considered as a initial wear region. Now next one is a tool life. So generally at different levels, different definitions of tool life is given. Generally as a purpose of R&D or academics, it is defined as the actual machining time by which tool can work satisfactorily without its sharpening or its replacement. That means the span of time up to which you can use tool without deviating its performance, that is the tool life. Generally that is in a minutes, say 5 minutes or 15 minutes or 75 minutes, that is the tool life. Whereas in industry, generally the tool life is defined as the total number of components machined. Means with this tool, suppose 10 components are machined, that means the tool life is 10 components. After that, you have to replace a tool, or you have to sharpen the edges of that tool. So that is the number of components that you have machined with a given tool, with a selected tool, that decides the tool life. Or you can also term a tool life in terms of volume removed. So the amount of volume removed in mm cube or centimeter cube, okay, from your workpiece in the form of chips, that is also can be defined as a tool life. Suppose with this tool you can remove 50 centimeter cube volume, so that may be the tool life. So in short, in general, we can define a tool life as it is a time elapsed between two successive regrinding or resharpening. That means the time up to which your tool will work satisfactorily, and then you have to sharpen the edges. So that time is the tool life, and generally this time is measured in minutes. So tool life is generally in a minutes, say 60 minutes, say 75 minutes. Okay, so there are various means through which you can express a tool life. So one is in time unit. Say the tool life of this tool is 30 minutes. The another measure is the number of components. Say the tool life of this tool is 50 components. That means it can machine 50 components. Then you have to replace the tool or restart the tool. Tool life can also be expressed in terms of total volume removed by the tool from the workpiece, or tool life can also be expressed in the term of total length of cut during the machining. So these are the different ways through which you can define a tool life. The next one is the tool life equation. The scientist W.F. Taylor has derived an equation that relates the cutting speed with tool life, that is V T raised to N is equal to C constant. Now to derive this expression, he has tried to relate the cutting velocities with a tool life. So by considering the profile of wear, you can see here in figure, suppose on an x-axis there is tool life and on a y-axis there is flank wear. So if at a different type of machining, suppose at some time here, at another time here, at another time here, at another time here, if this different time you are measuring the flank wear in mm, okay, so at some time this flank wear value reaches to a value of 0.3 mm. So that is the deciding criteria. Whenever your flank wear reaches to a value of 0.3 mm, at that time it is considered that tool life is get over. So this time T1 is the tool life at a cutting speed of VC1. Now suppose I am increasing cutting velocity VC2, that is greater than VC1. So it is obvious that if you are increasing cutting velocity, then the wearing takes place at a rapid rate, and the time taken to reach the wear of 0.3 mm will reduce to T2 at the velocity Vc2. Again you are increasing the cutting velocity Vc3, that is greater than Vc2. So the velocity is increasing, that means the time needed to reach a tool to wear off at a 0.3 mm will again reduced, and your tool life will reduced to T3. Again if you are increasing cutting velocity Vc4, then the tool reaches to a wear of 0.3 mm very rapidly, and that is the time T4. So it shows that as you are increasing your cutting velocity, your tool life is decreasing. Okay, so if these velocities and the tool life is plotted as shown in this figure, so here you can see that the tool life in minute tool life t is on x-axis and the cutting velocity is on y-axis. So at different combination, as the cutting velocity is Vc1, that is the lower one, at the time you are getting the maximum tool life, so that is the T1. Okay, again, so this is the combination of Vc1 T1. Again you are increasing cutting velocity Vc2, then your tool life decreases here. Okay, so this is the combination of Vc2 and T2. Successively you are increasing your cutting velocity, then the tool life getting reduced. Again you are increasing the cutting velocity, then again you are getting reduced tool life. So this is the combination of Vc3 T3 and Vc4 and T4. So you can get the plot like this by plotting velocities on a y-axis and tool life on a x-axis, and by considering these points you can get the profile of your combination of velocities and tool life like this. So here you can easily see that as the cutting velocity increases, your tool life decreases. Now if this combination of velocities and tool life is plotted, now if the combination of these cutting velocities and tool life are plotted on a logarithmic scale, then you will get the graph like this, that is the linear line. So this is the combination of V1 T1, V2 T2, V3 T3, okay, and V4 T4. Okay, so here this is on x scale log t and y scale log Vc. So this is the straight line, and the slope of this straight line is tan alpha is equal to n. So n is the slope that is considered as a machine exponent that depends upon the tool material and workpiece material. Now if we try to write an equation for this line as y is equal to mx plus c, then we can write in such a way that suppose this is log vc, that is y is equal to slope n, that means n, then x, that means log t plus c. See, that is the intercept. That means suppose this is the log t value 1, so at one value of log t, the maximum value, that is the intercept, that is the c. Now here you can see that the time is on a opposite scale. Here this is t1 and here this is t4. That's why instead of t1 to t4, the time scale is t4 to t1 reverse side. So here log t scale is taken as a negative. Now if we simplify this formulae, then we can write in a combination like this: v t raised to n by removing log scale and defining the new constant, that is the c. So that is the v t raised to n is equal to c. That is the formula. Now here the c is the constant, okay, and that constant is depend upon the workpiece and tool material combination, that is the intercept, whereas n is the machining exponent that depends upon the type of tool material. The different values for different conditions can be obtained from the data book for the values of n and c. So here this formula relates the cutting velocity with tool life, that is vt raised to n is equal to. So there are different factors that affects the tool life of a tool. So first one is a machining parameters. So we have already seen that how the cutting speed affects the tool life. However, the effect of another two machining parameters, that are fade and depth of cut, is quite less, but we have to consider it. So the modified tool life equation is obtained by considering all three parameters, that are fade, speed and depth of cut. So the modified tool life equation is like TL is equal to constant c divided by cutting velocity v raised to x, feed raised to y, and depth of cut raised to z. So this is the modified formula for the tool life. So here the effect of cutting speed is quite more as compared to feed and depth of cut. So x, y and z are the weightage component. So generally the value of x is larger as compared to y and z. So generally x will always greater than y, will always greater than Z. The effect of cutting velocity is maximum, then the feed, and then the effect of depth of cut is on tool life. The another factor that affects uh, tool life, that is the type of cutting. So the one is the continuous cutting and another is the intermittent cutting. So if the cutting is continuous, then the tool life will be greater. But if the cutting is intermittent, then there may be the chance of sudden loading shocks on a tool due to the intermittent cuts, and the tool life may be poor in the case of intermittent cutting as compared to continuous cutting. The third factor that affects the tool life is tool material. So ideally, the tool material should be such that it can machine your workpiece material at any cutting speed without deviating its performance. So you can see that for the tool like high speed steel, the tool life will be in a range of 60 to 120 minutes. But if you are using a tool like a cemented carbide, then you can obtain a tool life up to 480 minutes or up to 500 minutes. Even with a diamond tool, you can get a tool life of this range. So the selection of tool material is also depend upon the tool life. The another factor is workpiece material. So what is your workpiece material that also affects the tool life? The physical properties of workpiece material, the hardness, the strength, the toughness of your workpiece material. Okay. The microstructure of workpiece material. If we are talking about the machining of steel material, then there may be various phases are present like perlite, sorbite, trustite, martensite. So we know the perlite is the softest element in a microstructure, whereas the martensite phase is the hardest one. So in your steel, in microstructure, if the constituent of martensite phase is more, then the workpiece material may be hard, and to machine that component, larger cutting forces is required, and at that time there are chances that the tool life is quite lower when you are dealing with a material having a martensite like phases as compared to a phase of perlite. The another factor is tool geometry. So in which range your tool angles are present in your tool may also affect the tool life. Simple. Suppose you have a tool with a positive rack angle. That means at a positive rack angle, the chip will flow easily because it has a larger space to flow away. So there will be a laser interaction between rack surface and your chip. So at that time, it may happen that due to laser friction, the plastic deformation of tool may not happen and the tool life may increase. as in case of negative rect tools, this is reverse. There is larger interaction because of the negative rect surface and the larger local temperature, and that may result in a plastic deformation causing a failure of tool life. But the another thing is that the rack angle also defines the tool strength. Lower the rack angle, that means if the negative rack angle, then the included wedge angle will increase, and that gives the more strength to a tool. Whereas if the angle is positive and it's large, then the included wedge angle will be reduced, and that may result in a lower strength of tool, and that may also causes the failure of tool. If we talk about the relief angle, if smaller the relief angle, then at the flank surface there is the chances with the machine surface of friction is quite larger. But if clearance or relief angle is larger, then your flank surface may not rub with your machine surface, which leads to a improved tool life. So in this way, the various angles have a role to modify or to improve the tool life. Even a side cutting edge angle or primary cutting edge angle also contributes to a tool life. Tool with a larger cutting angle will gives more tool life as compared to a tool with a smaller primary cutting edge angle. Because with a large angle, the surface of the tool increases to bear the load exerted by the workpiece during a chip, that we have discussed earlier at the time of tool geometry. And the next thing is that the use of cutting fluid also contributes in a tool life. Effective use of cutting fluid may improve tool life. The next one is the machinability. Now what happens? During a chip formation, sometimes we deal with a workpiece material in which we can form chip easily, while for some other materials there is a greater difficulty for the chip formation. So this difference of ease in chip formation can be attributed as a machinability. So basically machinability is the ease of machining. Okay. So it is a comparative index. It gives an comparative idea of a workpiece material for which you are working with respect to some other standard material. So we can define machinability as the ease with which metal is cut satisfactorily for the purpose intended. Okay, so that is the machinability. So what is good machinability? So if during machining the cutting forces are moderate, okay, the chips are forming that are smaller in size or constant, and the surface finish that is obtained is good, and there isn't any excessive tool wear, then we can consider that the machining condition is good. Okay. So it again depends upon the various factors. First of all, workpiece material. So the physical property of material like hardness, toughness, okay, the microstructure of the material, so that all affects the machinability or ease of chip formation during a machining. Suppose I say that the material A is quite good machinable as compared to material B. Okay, so what it means? It means that while we are doing the machining of material A, the forces that are involved during cutting are quite less. The other thing, while we are machining material A, then it gives good surface finish as compared to material B. And with dealing with the material A, the tool has a longer tool life as compared to a machining with material B. So in such a way, we can compare the machinability of different materials. So there is one relative index defined to relate different workpiece material with some standard material in terms of its ease of chip formation. Okay, so machinability index I in percentage is the ratio of Vi by Vs. Now what is Vi and what is Vs? So Vi is the cutting speed of metal investigated for 60 minutes of tool life. So Vi stands for the material under investigation. So for that material, when the tool life reaches to 60 minutes, that cutting speed is considered as a Vi. Whereas Vs, that is the standard material. Okay. So Vs is the cutting speed of the standard material or standard steel for 60 minutes of tool life. So for that standard material, at which speed the tool life of 60 minutes can be obtained, that speed is considered as a speed of standard material. Okay, and the ratio of these two gives the machinability index. So let me give one example. 1 second. So here you can see that this is the standard material. So standard material is taken as AISI 1112 steel. Okay, and this is the specimen material which is under investigation. So here the cutting speed versus tool life are plotted. So at various cutting speeds, what are the tool life that is drawn, and this line is obtained for the standard material. So for standard material, at a speed of 100 RPM cutting velocity, the tool gets a tool life of 60 minutes. And for a specimen material that is under investigation, okay, at a cutting velocity of 60 RPM, the tool life of 60 minutes obtained. So here we can write that machinability index I is equal to Vi divided by Vs. So Vi, the velocity of specimen material or material under investigation, and the speed at which the tool life of 60 minutes obtained. So that speed for the specimen or investigated material is 60, whereas the standard material, the speed that is 100 at which it get a tool life of 60 minutes, that is 100. So 0.6, that means 60% is the machinability of the workpiece material under investigation. Okay. So in this way you can compare the machinability of different workpiece material with respect to standard steel, that is AISI 1112. Here some problems are given for your practice, so kindly try to solve it with the reference of the discussion we had in present lecture. So thank you.